Welcome to today's deep dive. We're really thrilled to have you joining us.
Absolutely. It's great to be here.
So to kick things off, I want you to consider one of the oldest, maybe the most profound questions humanity has ever asked. Are we alone in the universe?
It's a heavy one.
Right. I mean, for centuries, we've been pointing telescopes at distant galaxies, building these massive radio antennas, just hoping to catch a signal from the stars. But what if we've been looking in the wrong direction?
Yeah, what if the answer is right under our noses?
Exactly. What if an equally profound mystery, an entirely alien world of communication, is right here on Earth, hidden in the voices of the animals all around us?
It's a completely paradigm-shifting thought. We are so conditioned to look up, out into the vacuum of space that we often forget to look down and deeply analyze the acoustic environment of the world we're actually standing on.
And that brings us to today's stack of sources. We're diving into a fascinating publication from today, actually March 6, 2026, titled Decoding Animal Communication with AI.
It is a phenomenal piece of work.
It really is. It's packed with references to groundbreaking documentaries, books, and recent work from major scientific institutes. Our mission for this deep dive is to explore how artificial intelligence is acting as basically a zoological version of Google Translate.
Right.
We're going to look at how it's unlocking a hidden world of digital bioacoustics, what this means for our relationship with nature, and believe it or not, what it means for our search for alien life.
We're really approaching a moment where humanity's long-held assumption that we are the only species on this planet capable of complex communication is about to be heavily scrutinized,
Yeah.
if not entirely shattered. I'm really looking forward to unpacking the methodologies driving this shift.
Same here. To ground us in the material, I want to describe the very first image included in our source text. It's a serene forest scene.
It's a beautiful illustration.
Yeah, so there's a wooden cabin with a golden retriever resting on the porch. On a branch in the foreground, there's a bird perched there, and in the distance, you can see the ocean with a whale breaching the surface.
And then there's that visual thread tying it all together.
Exactly. Connecting all of them, the dog, the bird, the whale, the forest itself, is this glowing, high-tech blue audio wave pulsing right through the air. It's a striking visual representation of the invisible communication network we're about to explore.
That image effectively captures the essence of the current scientific pivot. The acoustic network has always existed. The variable that has changed is our capacity to process it.
Okay, let's unpack this. Because the way we collect data about animals has dramatically transformed. We are far beyond the era of, a dedicated biologist sitting in a blind with binoculars and a notebook.
Thankfully.
Right. Today, we have hydrophone arrays dropped into the deepest ocean trenches, biologgers attached directly to migrating animals, drones mapping dense forest canopies. I mean, there are acoustic sensors scattered across entire landscapes.
And the sheer volume of data coming from all that is staggering. The challenge for modern biology is no longer collecting the signals. We have petabytes of ecological audio just sitting on servers.
So it's about making sense of it.
Precisely. The bottleneck has been analysis. This is what Dr. Karen Baker termed the digital bioacoustics revolution in her 2023 book, The Sounds of Life.
Great book, by the way.
Incredible book. We've deployed the sensors to detect signals from the natural world, but making sense of that data requires computational power that humans simply do not possess natively.
The examples in the text really highlight the scale of what we've been missing, too. Elephants, for instance. They communicate using infrasound that travels for kilometers through the ground.
Yeah.
They are effectively talking to each other through the earth beneath their feet. Then you have marine ecosystems. Fish are producing complex acoustic patterns we previously assumed didn't exist. The text even notes that stressed plants emit ultrasonic clicks.
What's fascinating here is how these discoveries highlight our own biological hardware limitations. The limitation wasn't that animals and plants weren't communicating. It was that human auditory processing is incredibly narrow.
We're practically deaf to most of the planet.
Exactly. We simply couldn't detect the frequencies, let alone parse the patterns. AI is rapidly becoming the synthetic processing center that bridges that gap. It allows us to find syntax in what we previously categorized as ambient noise.
But how do we avoid the trap of anthropomorphizing that noise? Because we've known animals make sounds forever. The text mentions Kon Slobodchikov, an animal behaviorist who founded the Animal Language Institute, and his startup, Zoolingua.
Right, focusing on dogs.
Yeah, he's looking at dog vocalizations and body language to find patterns. But how does an AI differentiate between a dog conveying complex contextual information and a dog just reacting instinctively to a stimulus?
That is the foundational hurdle of this entire field. You can't just assign an English word to a dog's bark and call it a translation. That's where the Earth Species Project, or ESP, comes in.
Tell us about them.
ESP is a nonprofit bringing together experts in artificial intelligence, neuroscience, linguistics, mathematics, and ecology. Their mission is to decode non-human communication without prior human interpretation.
The text references a session from the World Government Summit in 2024 featuring Jane Lawton, the Director of Impact at ESP. And what stood out to me is that they aren't trying to build a traditional dictionary.
No, not at all.
They're aiming to translate human language directly into the communication systems of other species. What does that actually look like in practice?
They are utilizing multidimensional spatial models. So in machine learning, specifically with large language models, AI maps human language by placing concepts into a multidimensional geometric space, a latent space.
Okay.
Words that share relational context end up physically closer together in this mathematical structure. What ESP hypothesizes is that the geometric shape of language might be universal.
Whoa, so across species.
Yes, if you map the latent space of human language and then map the latent space of, say, primate vocalizations, the AI might be able to rotate and overlay those shapes to find intersecting nodes of meaning. This is completely independent of a human linguist trying to guess what a specific grunt means.
That is a massive conceptual leap. They are looking for the fundamental mathematics of communication, regardless of the biological source.
Precisely. And that methodology is being applied with laser focus right now by the Cetacean Translation Initiative, or CEE, founded in 2020 by biologist David Gruber.
They focus on sperm whales, right?
They do. They're zeroing in on sperm whales, which are highly socially complex animals. Sperm whales communicate using structured sequences of broadband clicks called codas.
The text notes that these codas vary between different whale groups, acting almost like regional dialects, but the ocean is notoriously noisy. How is CEE actually gathering clean enough data to map a latent space for whales?
It requires extreme precision. CEE deploys vast underwater hydrophone arrays and drone swarms to triangulate exactly which whale in a pod is emitting a specific coda.
Wow.
Yeah, they correlate the acoustic data with high-resolution behavioral and positional data. They aren't just recording the sound. They were recording the three-dimensional context in which the sound is made.
And then feeding that to the AI.
Exactly. They feed this multimodal data into advanced machine learning models to identify rules of syntax. They're searching for the structural framework of a conversation.
So what does this all mean? For you listening right now, if CDI succeeds, it represents the first serious, scientifically rigorous attempt to translate the communication of another intelligent species.
It completely redefines our understanding of intelligence hierarchies on Earth.
It really does.
It forces a philosophical recalibration. If we prove the existence of grammar and syntax and the clicks of a sperm whale, the traditional anthropocentric view of intelligence becomes obsolete. We have to acknowledge a horizontal distribution of cognitive complexity.
Here's where it gets really interesting, because as much as this research is about understanding our oceans, the source material pivots to how this directly connects to outer space.
Yes, the SETI connection.
The methodology being developed to talk to whales is actively serving as a dress rehearsal for communicating with extraterrestrial intelligence.
The connection seems like science fiction, until you look at the underlying math. The text details a recent, highly significant experiment involving the SETI Institute, UC Davis, and the Alaska Whale Foundation. They conducted an interactive acoustic exchange with a humpback whale named Twain.
I want to break down how this encounter actually worked. Researchers on a boat used an underwater speaker to play a recorded humpback contact call into the water. Twain, the humpback whale, didn't just passively listen.
Not at all.
The whale approached the research boat and engaged in a 20-minute rhythmic exchange.
The critical data point from that exchange is the phase-locking behavior. When the researchers played the call, Twain replied. When the researchers adjusted the timing interval of their playback, Twain mirrored that adjustment.
That's incredible.
It is. The whale was actively matching the delay intervals of the human-generated signal.
Why is that specific interval matching so important to the SETI Institute?
If we connect this to the bigger picture, it addresses a fundamental problem in astrophysics. Lawrence Doyle, a SETI scientist referenced in the text, notes that the core challenge of searching for extraterrestrial intelligence is recognizing a meaningful signal within a vast sea of cosmic noise.
Because space is full of random radiation and noise.
Right. If we receive a message from deep space, we will not share any biological or cultural context with the sender.
We won't have a Rosetta Stone for an alien civilization.
Exactly. One of the biggest working assumptions in SETI research is that an intelligent being would deliberately structure a signal to demonstrate communicative intent. The encounter with Twain offers experimental validation for this.
Because Twain altered his response based on what he was hearing.
Yes, Twain heard an unfamiliar acoustic pattern and was motivated to respond, to match the rhythm, to engage in an interactive loop. It suggests that curiosity and the desire to reach across a communication barrier are not uniquely human traits. They might be universal markers of intelligence.
But why are we focusing so heavily on whales for this interstellar practice? The text outlines this by referencing a 2021 documentary called Fathom, which features Dr. Michelle Fournet and Dr. Ellen Garland. Humpback whales have enormous brains, sure, but they also produce these incredibly long, structured songs that can travel across entire ocean basins.
They also demonstrate robust cultural transmission. Whale songs evolve over time. New acoustic patterns are introduced in one population and spread horizontally across different pods, much like the transmission of slang in human societies.
The behavioral intelligence is equally striking. The text mentions bubble net feeding, which requires intense coordination.
Bubble net feeding is a perfect example of acoustic utility. It's a cooperative hunting strategy where multiple whales release synchronized rings of bubbles to trap schools of fish, forcing them to the surface.
Like a net made of air.
Exactly. This isn't just instinctual schooling. It requires a lead whale to issue highly structured harmonic feeding calls that coordinate the physical positioning and timing of the entire pod. To make sense of that level of acoustic richness, scientists are applying information theory to the data.
Let's dive into information theory because the text emphasizes this as the crucial mathematical link between bioacoustics and astrophysics. How does information theory help us decode a whale's hunting call or a potential alien transmission?
Information theory, originally developed by Claude Shannon to optimize telecommunications, is essentially the mathematics of data transmission. It measures something called entropy, which in this context means predictability.
Okay.
If a signal is entirely random, its entropy is too high. It's just noise. If a signal is entirely predictable, like a metronome, its entropy is too low. It carries no complex information.
So language has to sit somewhere in the middle. It requires structural rules, like grammar, but enough flexibility to convey complex, varying ideas.
That is the exact mathematical signature researchers are looking for. By applying information theory to whale code, as scientists are analyzing the acoustic entropy of the clicks, they are practicing the exact mathematical techniques that will be required to process and decode anomalous radio bursts detected from deep space.
Wow.
If we cannot parse the entropy of an intelligent signal originating from a species in our own oceans, our chances of parsing a signal from a civilization light years away are statistically zero.
The implications are massive, but with any technological leap of this magnitude, there are serious consequences. Let's look at the ethics of interspecies translation.
We have to.
Because the bright side is incredibly inspiring for you, the listener. The potential to transform wildlife conservation is immense. If we can process and understand animal signals in real time, we could detect ecosystem distress, disease outbreaks, or environmental threats far earlier.
Absolutely.
Veterinarians could use diagnostic models trained on the vocalizations of domesticated animals to vastly improve care. It could fundamentally deepen human empathy toward the natural world.
This raises an important question regarding the dual-use nature of foundational AI models. The text is explicit that we must balance optimism with rigorous caution.
We always have to be careful with new tech.
Historically, whenever humans have gained deeper technological access to the natural world, exploitation has rapidly followed. The dark side of digital bioacoustics is significant.
The potential for manipulation stands out immediately. If we understand the exact syntax of a humpback whale's contact call or a bird's mating song, what stops someone from using that synthetic generation to lure animals?
Very little under current regulatory frameworks. The acoustic mapping could be easily weaponized by poachers or illegal fishing operations to artificially aggregate endangered species.
That's terrifying.
It is. Furthermore, consider the agricultural sector. If AI can translate the specific stress signals of livestock, There is legitimate concern that this data might not be used to improve animal welfare, but rather to calculate the exact threshold of stress an animal can endure to maximize industrial farming efficiency.
Just squeezing out every last drop of productivity. The text also touches on the long, troubling history of animals being utilized in warfare, suggesting that deciphering communication networks could open new avenues for military applications.
The ultimate challenge highlighted by the scientific community in the source material is one of governance. This breakthrough will grant humanity an unprecedented level of influence over other species.
Yeah.
The technological capability is inevitable. The models are already training. The true test will be ensuring that this newfound data is utilized to establish sustainable coexistence rather than accelerating ecological extraction.
It's a profound responsibility. As we bring this deep dive to a close, I want to leave you with the final image described in our source text. Picture a researcher sitting out in nature, wearing a pair of advanced headphones connected to a bioacoustic model.
I love this imagery.
It's so powerful. They aren't just listening to ambient noise. They are tuning in to the structured conversations of the earth. They hear the syntactic clicks of whales in the water, the culturally transmitted calls of birds in the air, the infrasonic rumbles of elephants vibrating on the shore, and the subtle chemical acoustic signals of glowing fungal networks beneath the forest floor.
It represents a definitive philosophical shift. For the entirety of recorded human history, we have placed ourselves at the absolute pinnacle of a hierarchy, operating under the assumption that we were the sole operators of complex, meaningful communication.
Right, that everything else was just instinct.
We view the rest of the planet as largely instinctual and relatively quiet.
But the data proves it's not quiet at all. Birds are passing evolving songs across continents. Elephants are maintaining long-distance social networks through the dirt. Forests are dynamically reacting and signaling through underground networks. The Earth is a continuous, complex symphony of data exchange.
Artificial intelligence is simply the translation mechanism revealing a biological truth that has existed for millions of years. We were never alone in our capacity for language on this planet. We simply lacked the computational tools to listen.
Yeah.
Acknowledging that intelligence and syntax can be expressed in entirely non-human architectures is the necessary first step toward redefining our relationship with the living world.
It completely reframes how you look at the natural world around you. So, as you go about your day, we want to leave you with a final provocative thought to mull over, building on the methodologies we've explored today. If AI finally allows us to parse the syntax of the natural world, to accurately decode the complex structures of their communication, are we truly prepared for what they might have to say about us?
That is the real question.
Thanks for joining us on this deep dive. Keep listening, keep questioning, and we'll catch you next time.